Really excited to invite our next speaker up. It's Kirsten Trinidad. She's a PhD student at the Tufts University's Center for Cellular Agriculture, and we're so happy to have her here after a tough journey, I've heard. She's going to be opening up our couple of sessions regarding LCAs and populating those inventories that we need so much to do this work.
Thank you so much. Is this working? Is it working? Okay, cool. Hi, everyone. My name is Kirsten Trinidad. I am a PhD candidate in Dr. David Kaplan's lab over at Tufts University. And today I'm here to present to you a recently published life cycle assessment performed by myself, Reina Ashizawa, Dr. Amin Nika, and Dr. Nicole Tishner-Blackstone on recombinant protein production for cultivated meat LCA applications. So throughout the talks yesterday, they really emphasized that cell culture media is a necessary input for cultivated meat applications. However, the production of the components that make up cell culture media has been deemed a hotspot in life cycle assessment or LCA literature. A hotspot is a process that has large contributions to the total environmental impact of a production system, and life cycle assessment is a standardized, widely used method to quantify and estimate the environmental impacts of products and processes across their life cycles, from raw material extraction all the way to a designated end stage or final product, otherwise referred to as a functional unit. And so within the cultivated meat LCA literature, recombinant proteins in cell culture media have been significant drivers of environmental burden, despite usage in low concentrations. Growth factors specifically are recombinant proteins that are critical to serum-supplemented and serum-free media formulations used currently for cultivated meat production. However, their production process environmental impacts have been excluded from system boundaries in previously published LCAs. They have been estimated using proxies, or they have been modeled based on proprietary data. And so this unavailability of data may decrease the level of accuracy of each LCA study, which may in turn inaccurately inform decisions ranging from sustainable media development all the way to consumer acceptance studies, in which environmental sustainability, as you all know, is a huge driver for this nascent technology's commercialization. And so LCA methodology was applied to comparatively assess the environmental impacts of 4 culture meat relevant growth factors. And this study aimed to construct publicly available bench scale life cycle inventories, or LCIs, of specifically IGF-1, FGF, TGF-beta, and PDGF, using primary data from our collaborators over at the University of Calgary. And by providing these data open source and by providing them to the public, we hope to provide LCA practitioners as well as other cultivated meat researchers with high quality data in order to create more accurate LCAs in the future. So the scope of this particular project is outlined here in this product system diagram, which outlines the 5 major processes of growth factor production, again created and validated by our collaborators over at the University of Calgary. And the 5 main steps, also known as unit processes in LCA jargon, involves scale-up protein expression, which is the proliferation of growth factor producing E. coli cells, followed by their lysis in order to release the growth factors because they are intracellularly produced in this process, followed by purification, cleavage of the tagged proteins, and then another step of purification afterwards to then amount to a functional unit of 1 milligram of purified growth factor to which all inputs were normalized to. In order to conduct these studies, OpenLCA and EcoInvent software and databases were used. Impact assessment was calculated using the recipe midpoint 2016 H method, and the impact categories chosen to go deeper into was global warming potential, water consumption, marine and freshwater eutrophication, stratospheric ozone depletion, terrestrial acidification, and fine particulate matter formation, all impact categories relevant to food systems. In terms of results, so this figure shows the environmental contributions of each of the 4 different growth factor production systems. So all the growth factors were produced using the same streamlined bench scale process. And so the differences in impact are due to differences in product yield, with FGF yielding having the most purified protein yield at the end of the production process, meaning that it has the least environmental impact, whereas PDGF yielded the least amount of purified protein at the end of the production process, yielding, causing the most environmental impact. And so we can conclude that the environmental impacts of growth factors are yield dependent. We wanted to dive deeper into a specific growth factor, IGF-1, for the remainder of our studies, as it is used commonly in cell culture media. And we wanted to understand what exactly and what part of the unit process contributed to the significant environmental burdens. And so we divided the study into the 5 different unit processes and determined that electricity usage and substrate consumption were the largest contributors to environmental burden for all impact categories. Looking into the upstream process of fermentation for global warming potential specifically, a lot of that impact was attributed to electricity usage due to overnight incubation steps and mixing. And then looking more into downstream processing, post-elution actually contributed to 33% of the overall global warming potential burden of this particular process. So in LCA, uncertainty of results can be conducted through something called sensitivity analysis. And for this example, we chose to highlight sensitivity of our system using 4 key inputs and fluctuating their input values by plus or minus 10%. And so as seen in this heat map, all impacts neither decrease nor increase beyond 10% in respect to the baseline condition, with the exception of electricity. And because of the significant change in category or impacts for electricity, we wanted to kind of explore how robust our model was when using different electricity scenarios. So our baseline electricity scenario was based on the west coast of the United States, as we assume that the West Coast is a huge hub for cultivated meat production. But we also wanted to compare and have a whole holistic view of the United States in terms of electricity mixes. And so we compared it against the Midwest electricity grid mix as well as the Northeast electricity grid mix, which differs in terms of the ratios of renewable energy and fossil energy, things like that. And so we have found that MRO, or the Midwest, represented the worst performance and NPCC the best. There were quite significant differences, and I think this is super interesting considering production of cultured meat has yet to, become large scale. And a question that is definitely had is where exactly to put these production facilities. And we could see how different electricity scenarios or grid mixes can significantly change the environmental impacts of a production process. The second scenario that we wanted to kind of dive deeper into was based off of our finding that the post-elution step occurring after the first purification of the growth factors contributed to a whopping 33% of the environmental impacts, which is a lot for global warming potential. And so with our collaborators over at the University of Calgary, so we suggested some studies, cell culture studies be done using a less purified version of the growth factor. So just using the growth factor with the using the fusion protein for the cell culture studies without cleaving off that his tag, without cleaving off the his tag, and seeing how it does in terms of cell culture studies within the cell culture media. And we have seen that the primary data demonstrates that it works just as well as the double purified protein. And because of that, we reran our analysis and found that impacts across all impact categories were seen to decrease by 46%, which kind of points to the importance of food grade purification versus pharmaceutical grade purification for cell culture media, with food grade purification having significantly less impacts, potentially. And so to conclude, it's difficult, of course, to estimate the potential contribution of these growth factors due to differences in scale, reported media use efficiencies, as well as different requirements for cell culture media. But when comparing these results against previously published LCAs, we can conclude that the impacts of growth factor production could be non-negligible, falling between 0.4 to 23% of the total global warming potential impacts. Before the acknowledgement slides, I would like to shamelessly plug some other work that I do outside of this. I come from Tufts University, and something that I think is really important is transparent education. And I think, you know, being part of university, we are put in this very special position that, you know, people come to us for transparency. And so some of the USDA-funded education efforts that I help lead at Tufts University include social media platforms as to transparently communicate what cell ag is, educate the general public on different papers, like how to break down a paper, offer free seminars for those interested in this nascent field. I also help run a seminar series. Our next seminar is happening on October 27th. I know people around here are probably not from the East Coast of the United States, but if you're able to make it and it's not an egregious time for you, our next seminar is from 12 to 1 p.m. Eastern Standard Time on October 27th, featuring a very excited speaker, Alan Pearlstein. Dr. Mark Post actually was a keynote for one of our previous Cultivate seminars last year, so still going with this, still going on strong. And feel free to follow us at Cell Agram on Instagram, run by Kevin and Olivia, who are undergrads that are here. They really help with promoting the social aspect of the work that we do, as well as the work that a lot of other institutions within the United States do. And with that being said, I would like to close my talk by thanking all of my collaborators, Raina, Dr. Amineka, Dr. Nicole Tishner-Blackstone, and Dr. David Kaplan, as well as all of the current and past grad students, postdocs, and research techs. Our paper, as I said before, is published, so feel free to scan the QR code to read more, and thank you.
You guys should too. Any questions? Front and center.
Hello. Thank you for the talk. It was so interesting. I am wondering if you could just explain a bit deeper on, for each impact category, how your results translated into the scores you showed.
Yeah, good question. So LCIA, which is a life cycle impact assessment, can be used to essentially translate the burdens into specific impact categories using something called a characterization factor. So what is a characterization factor? A characterization factor is the environmental impact associated with a unit of stressor. A stressor for the different impact categories is something like, so for example, global warming potential, a major stressor for that or indicator of that is methane emission as well as carbon dioxide. For marine eutrophication, it's things like ammonia and nitrous oxide and nitrogen. Freshwater eutrophication, things like phosphorus. So all of these emissions have major impacts on those impact categories, and a characterization factor basically weighs out certain emissions to be heavier instead of like other emissions. So when I'm running these analyses or running the model, I get a certain output, and that output is multiplied by the characterization factor, so all of the emissions are normalized and can be added together to create an overall score.
Thank you.
Thanks for that explanation. That was really helpful, I think. Unfortunately, we are right at the end of our time, so if you have any questions, maybe you can talk to Kirsten directly.
Thank you.